Hey everyone. So in this quarter so far, we've plotted a lot of histograms, and most of them have kind of had this sort of bell shape to them, and so we've called them bell curves. A deep question in statistics is, why do we see that so often, and when can we expect to see that? And that's a question we're going to answer in the second part of the lecture. In the first part of the lecture, we're going to give a name to this bell curve. We're going to call it a normal curve, or a Gaussian. You may have heard this term before. And we're going to study some of the properties of this curve. So let's start off with a data set that's going to give us a bell curve. Here I have the height and weight of 5,000 people who identify as male. And you see I have a table here, 5,000 rows, 2 columns, height and weight. Let's plot just the heights as a histogram. Let's visualize the distribution of the heights. So here's our histogram. We see that it has this bell shape. It's roughly symmetric. And it looks like the mean of this distribution is at about 68 inches. If I look at the weights, I'm going to see something similar. So I'm just going to plot the distribution of the weight column. It's pretty much the same shape, but you'll notice there are some differences. So if I go back and forth between these two, it's pretty much the same shape, but notice that the weights are centered up around, say, 180 or 190. And the width is different. So your plotting software can kind of fool you sometimes. If you look at these two, they look pretty much like they're the same width, but you have to notice that the x-axis has a different scale between these two. So the width here, so I'm going to go from like the bulk of the distribution seems to go between like 160 and 220, so that's a width of like 60 units. Here I'm going from like 65 to 75, so that's a width of like 10 units. So we've seen this shape over and over and over again, and every time we see this shape, the only thing different about it between two different times we see the shape is where that shape is centered and how wide it is. So let's plot these two histograms on the same scale. We see that I have the histogram for the heights here, the histogram for the weights here. They have the same general shape, but one is just kind of squashed, it's narrower, and it's centered to the left, that's the heights. And the weights are kind of stretched out and centered to the right. So it turns out that we have a procedure for taking these two distributions and removing sort of what's different about them, meaning where they're centered and how wide they are. And after I account for those two things, the distributions will be pretty much exactly the same. They'll overlap. So to account for the distance between them, the centering difference, I'm going to do what's called centering the data, meaning I'm going to remove any information about where the distribution is centered. And I can do that by subtracting the mean. So if you think about this, I'm going to take all of the heights, and for every height in my data set, I'm going to subtract the average height. And what that's going to do is it's going to shift that blue histogram to 0, so that the center is at 0, and then I have some heights which are positive, some which are negative. So let's go ahead and do that. I'm going to calculate the mean height here, the mean of the height column, 69.02 inches. I'll do the same for the weights while I'm at it. That's 187 pounds, I'm assuming. And then I'm going to insert them into the table. So I'll take my height column, I'll subtract the mean height. So I'm going to get a centered height column. Let's take a look at the result of that. So I've got a new table here called centered height and weight. Okay, so I've created a totally new table. You'll notice that the heights now are kind of centered around 0. I see some of them which are negative, some of them which are positive. If I go back and take the mean of the height column, guess what you're going to get? So I'll get the height, I'll take the mean of the height column. I get some number which is very, very, very close to 0. And mathematically, it should be 0, but remember we have some precision errors whenever we're calculating with floating point numbers. So they have limited precision, which means this is essentially 0. It's not exactly equal to 0, but it should be. Okay, so if I did the same with the weights should also be 0, but you notice that the weights are kind of more spread out, they're more variable. So this is what we get after centering. Now suppose I plotted the new distributions, plotted the new histograms after subtracting the mean. Here's what I get. those two distributions are now kind of centered at the same place, at 0. And now the only difference between them is how wide they are. So how do we account for their width? So the natural thing to do here is to divide by the width, so that the width becomes 1 for both distributions. And remember from last lecture, the way that we quantify width, oftentimes in statistics, is by using the standard deviation. So let's try it out. Let's compute the standard deviation of the heights, and then divide every height in my data set by that standard deviation. So I'm going to take the standard deviation, that's 2.86. So if I go back here and kind of look, I'm calculating the width here, the standard deviation of this. It's, remember, the square root of the variance, so it's not exactly, finding a point here, and finding the width of that, but you can kind of approximate it by saying, how big is this distance here? So it looks like it's about 2. On the other hand, let's try to guess what the standard deviation of the weights is. I'm going to guess it's about 25. Okay. It's about 20. Okay, so I was off by 5, but not too bad. And so let's take our centered heights and centered weights and divide them by their standard deviations. So now I get a new table. Let's call it standardized. Let's take a look at this table. So I have heights here, which are centered at 0. They don't look too much different than what I had before. I can't see much of a difference. That's because I only divided by about 2.8. But the weights, you notice, are much less variable now. Okay, and there's actually, if you look at these two columns, there's not too much of a difference between the two. You can't see that one looks more variable than another. And in fact, they're about the same. If I plot one on top of the other, I get two histograms which look almost identical, except for like little things here and there. Okay, and what I've done is I've taken the two distributions, which were each bell curves, and I accounted for their difference in location and their difference in width. And after I kind of account for those two things by centering and dividing by the standard deviation, I get a bell curve that is centered at 0 and has the same sort of standard width, which is, if I compute the standard deviation of each of these distributions, it's going to be 1. Let's try that out. So I take my standardized data, let's get the heights, and let's compute the standard deviation. There is no NumPy standard deviation. How about that? Yeah, it's exactly 1. Okay. Same thing for the weights. So this shape that is a bell curve centered at 0 and has standard deviation 1 has a special name. We call it the standard normal curve. And this is what this is sort of a formula for the standard normal curve right here. So if I want to plot a line which describes this shape, here's the function describing that line. It's 1 over square root of 2 pi, then I take e to the power minus 1 over 2, or minus 1/2 z squared, where z is the input to my function. So let's try to plot that. I've written a function here, a Python function, which just returns the value of the standard normal curve at any point x. So for instance, if I say normal curve of 0, what do you think it's going to be? I go back here, take a look. It should be something around here, like 0.4. Yeah, 0.39. If I make this number really large, you can imagine what it's going to be. It's going to be very close to 0. In fact, in this case, exactly 0. Same if I make it negative. And it's symmetric, so if I compute normal curve of 1, it's going to give me the same thing as normal curve of minus 1. So let's plot that curve. Okay, so I'm just using some NumPy functions that we haven't really talked about. This actually just generates a bunch of numbers. Between minus 4 and 4, it generates 1,000 numbers equally spaced. And then this function evaluates all of those input x's, so I get an array of output y's, and then I'll plot it. We haven't talked about these functions, but if you're curious, you can look them up. This is from matplotlib, plot.plot. And we see here's the normal curve. Here's our mathematical function which describes that standard, that standard bell curve, centered at 0 with a standard deviation of 1. In fact, this does a pretty good job of describing our data. Let me plot that mathematical function on top of our standardized distributions for height and weight. And you see it describes it really well. So let's talk a little bit more about the normal distribution, because it's a very, very, very important thing in statistics. So first of all, this line, this curve that we call the normal curve, you can think of it in some sense as a continuous histogram. The technical term for it is probability density. But what it is it describes the likelihood of seeing any particular value. The way that you get a probability, so remember from a histogram you can get the probability that a weight is a certain value by saying like, okay, what's the probability that, so let's go back to our original histograms here. I could say, what's the probability that a person in this data set is between 200 and 225? Well, then I would find the area of the histogram from 200 to 225, because that's the proportion of people that lie in that interval. Similarly, with the normal curve, what I can do is I can say, well, what's the probability that someone lies in this interval? And then what I do is I would integrate between here and here. Remember, integration is basically like summation. So a summation when I have infinitely many sort of bars in my histogram. So like a histogram, if I were to integrate over the entire thing from minus infinity to infinity, the total area would be 1, and the area between A and B is the probability of observing a value between A and B. Notice also the mean of this is 0, and the standard deviation, which we haven't talked about how to compute the standard deviation of like a curve, but the standard deviation would be 1 as well. So this picture kind of shows what I mean by computing the area between minus 2 in this case and minus a half. So this is the probability of seeing a value in this range.